Hey everyone, so we've learned all about infinite series, we've learned a bunch of tests. Now it's time to see, in some sense, why we might care about infinite series in the first place. So we'll start with this definition. A series of the form, so it'll be sum n equals 0 to infinity. It doesn't matter where the starting point is. I guess maybe more generally I should say n equals k to infinity c sub n x minus a raised to the n. You know what? For our purposes here, let me just start it at 0. It makes more sense. Sum n equals 0 to infinity. And now what would this look like? This would look like c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus dot dot dot, going on forever. And so what we'll have is a constant, and notice right here there's an x minus a to the 0, but x minus a to the 0 is just 1, so I didn't put that in there. So we've got a constant, then we have a constant times x minus a, constant times x minus a squared. The next one, in fact, let me write down a third term here, plus constant times x minus a cubed, plus dot dot dot. So this goes on forever. Right? This has a name. This is called a power series. Centered at A. One way to think of this, in fact, a useful way to think of this, right? So what do we have now? What we have is an infinite series, but it's got a variable in it now, a variable x. And so this should remind you of a polynomial, except it's a polynomial that doesn't stop. So I'll put this in quotes, right? You can think of a power series as an infinite polynomial. The study of power series is an extremely important part of math, and in some sense the reason that we learned about infinite series in the first place is so that we could study power series. So let me just give you an example. A first example, this will be sum n equals 0 to infinity x minus 2 to the n divided by n plus 1 squared. So what would this look like? This looks like, let's see, when n equals 0, I'm going to have 1. Plus, when n equals 1, I'm going to have 1/4 times x minus 2. Plus, okay, when n equals 2, I'm going to have 1/9 times x minus 2 squared. Sorry, I ran out of room. I'm going to write a couple more terms down here. The next one would be plus 1/16 x minus 2 cubed, 1/25 x minus 2 to the 4th plus dot dot dot. So that goes on forever. Right? But notice what this really looks like. It's a 1/9 there. What this really looks like is a polynomial that goes on forever. Another example. This one's kind of a famous example. Sum n equals 0 to infinity x to the n divided by n factorial. What would this one look like? Well, it would look like, remember, 0 factorial is equal to 1, so this would be a 1 plus an x over 1 factorial plus an x squared over 2 factorial, which is just 2, plus x cubed over 3 factorial, which is 6, plus x to the 4th over 4 factorial, which is 24, and then plus dot dot dot. That goes on forever. Now, one thing to notice, we'll say note, when a real number, an actual number, is substituted, in place of x, so substitute for x, what do we get? So for example, what if I just happen to plug in 3 for x into this example right here? Well, what I would get then is I would get 1 everywhere. What you get every time, I get 1, 1, 1, 1 in all those places. So it would turn into the series 1 over n plus 1 squared. And the point is, when you substitute a real number, what you get is a plain old ordinary infinite series, the ones that we've been studying for a while. So we get an ordinary infinite series. So for example, let's look at this one. And by the way, when I wrote down the original definition from a power series, I had n equals 0 to infinity, just to because I wanted to see the constant term there. It is not necessary to start at n equals 0. You can start at any n equals k, and it's still a power series. So in this example right here, so we'll have sum n equals 1 to infinity, x minus 1 to the n, divided by n times 2 to the n. Right? Now, what would this one look like? Let's see, when n equals 1, we just get x minus 1. When n equals 2, we get x minus 1 squared divided by 2 times 4. So what is that? 8 plus x minus 1 cubed divided by 3. I don't need to work this out, so it's 3 times 2 cubed, so I guess that would be 24, and so on. So now, let's see what happens if I plug in x equals 0. In that case, what we get is sum n equals 1 to infinity. So if I put a 0 in here, what we get is minus 1 to the n times 2n. This then gives us a convergent alternating series, right? So, you could use the alternating series test to show that it converges. If x equals 3, yep. If x equals 3, then what we will get is sum n equals 1 to infinity. So if I plug in x equals 3, what do I get here? I get 2 to the n in the top, 2 to the n right there. That will leave us, when they cancel, it'll leave us 1 over n. So this is diverges. Now this one diverges, or divergent. And the reason, p equals 1. So depending on the choices of x that you substitute in, right, you're going to get you'll get various infinite series, and then you can ask the question, for what choices of x does a particular power series converge or diverge? So let's write that down. Here's our general question. For what values of x does the power series sum n equals, I'll just use n equals k to infinity, c sub n x minus a to the n, converge or diverge? Now, it will always converge for at least one choice of x. When you choose x equal to a, what you'll get is sum 0 plus 0 plus 0 plus 0 is always convergent at the center a. And that's so every power series is convergent for at least one choice. In general, though, the way to answer this question is to use the ratio test. So let's look at the same example I was doing a minute ago. So that was sum n equals 1 to infinity. X minus 1 to the n over n times 2 to the n. All right, so our question is, for what values does it converge or diverge? And I'm going to apply the ratio test. So the ratio test says compute the limit as n goes to infinity. Absolute value x minus 1 up to the n plus 1 divided by n plus 1, 2 to the n plus 1 divided by x minus 1 to the n over n times 2 to the n. That's equal to the limit as n goes to infinity. I'm going to flip and multiply and then see how things cancel. So let's see, we'll have x minus 1 to the n plus 1, n plus 1, 2 to the n plus 1 times n 2 to the n over x minus 1 to the n. Okay, so I did flip and multiply. Now I'm going to cancel whatever cancels. And notice I can cancel some 2's and I can cancel some powers of x minus 1. So at the next stage, what we have is limit as n goes to infinity. So let's see, we'll have in our absolute value x minus 1 and an n. In the denominator, I will have a 2 and an n plus 1. Now, as n goes to infinity, notice that part right there approaches 1. And so what we're left with is absolute value of x minus 1 divided by 2. Now remember, we're applying the ratio test. And the ratio test tells us that we will get convergence, in fact, absolute convergence, although we're not going to worry about absolute convergence in this setting. We will get convergent whenever this limit is less than 1. So what we want to do then is identify the x values that make this less than 1. And so what we need then is for the absolute value of x minus 1 to be less than 2. I just multiplied this inequality by 2. To unravel an absolute value, what we'll have is minus 2 less than x minus 1 less than 2. And then if we add 1 everywhere, what we'll get is that x needs to be between -1 and 3. So we're guaranteed for any choice of x between -1 and 3, we have convergence. So convergent for -1 less than x less than 3, and divergent when x is strictly less than -1 or x strictly greater than 3, right? If the limit, as you take this limit when you're applying the ratio test, if you get something greater than 1, then you know that it's divergent. Now we have to remember, the ratio test is inconclusive at the endpoints. At the places, I shouldn't call them endpoints yet, but it's inconclusive at the places where we would get a limit of 1. And so, we now check the endpoints. All right? We know that we get less than 1 as long as we stay within this range. What if x is equal to -1? What if x is equal to 3? Well, if x equals -1, we already did this one, I think. If I plug a -1 in there, where'd it go? So when x equals -1, we have sum n equals 1 to infinity. This will be, it'll give us a -1 to the n over n. This converges by alternating series test. Hopefully everybody can just see that in their heads. If x equals 3, so let's see, if I plug a 3 in there, what we saw, right, so plug 3 into that power series, and what we'll get is some of 1 over n, and that diverges, right? That's with p equals 1. So the conclusion final conclusion is that our power series is convergent, and we write it this way on the interval from -1 to 3, where I include -1 and I exclude 3. If x is any number in this interval, then we're guaranteed that the power series converges. If not, then we're guaranteed that the power series diverges. And this is the way all of these are going to go. We're going to apply the ratio test. The ratio test, every once in a while I'll use the root test. I mean, in certain situations it's easier, but essentially I'm going to say virtually every single example I'm going to use the ratio test, and the steps are going to go exactly the same. Apply the ratio test, check the endpoints, write down the interval for which the power series converges. So let's look at this other example here. Sum n equals 0 to infinity, x to the n over n factorial. Once again, I'm going to apply the ratio test, and my question is, the general question, for what values of x does this power series converge or diverge? So I do the limit as n goes to infinity. I think we've all done this enough times now that we can just flip and multiply right away. And so I'm going to just do that. Hopefully you don't think of that as skipping too big of a step. All right, so I'm applying the ratio test. I already did my flipping and multiplying. Now let's cancel. So this is limit as n goes to infinity. Absolute value of x in the top and an n plus 1 in the bottom. Right? When we cancel the factorials, we're just left with an n plus 1. As n goes to infinity, that's equal to 0, right? Which is always less than 1, so no matter what choice of x, we get a limit of 0. That tells us that it converges for all choices of x, because no matter what x I plug in, I get 0, and the ratio test tells me that it converges. So, our power series, sum n equals 0 to infinity, x to the n over n factorial, converges on the interval from -infinity to infinity. It converges for all real numbers. Now, we've seen a couple of examples, and now I'm going to write down a general theorem. So no matter what power series we have, there are 3 possibilities. Right? So for the power series, sum n equals, I guess I'll say n equals k to infinity, c sub n x minus a to the n. There are 3 possibilities. First possibility, it's only convergent, so convergent only at x equals a. Right, that's sort of the worst possible situation. It only converges at the center. Other than that, it's divergent, so it's not an interesting power series. The second possibility, it's convergent for all real numbers. And then the third possibility, can I fit this all? Yeah. Okay. So the third possibility is there is a positive number r. Oh, let's write it like this, an r greater than 0. I want to be able to fit all of this into one line here. So there is r greater than 0 such that the series converges when absolute value of x minus a is strictly less than r, and diverges when absolute value of x minus a is greater than r. Okay, so one of those three things is guaranteed to happen no matter what. All right, anytime we have a power series, one of those three is going to happen. There's some words that go along with this theorem. So in case, in case 3, the number r has a name. R is called, all right, so in case 3, r is the, I don't even need to say in case 3. Let's just say it like this. R is the radius of convergence. So when 3 happens, we say, oh, this number r is called this is the radius of convergence of the power series. And in these other two cases, when case 1 happens, we say that the radius of convergence is 0. And in case 2, we say that the radius of convergence is infinity. So in case 1, we say r equals 0. In case 2, we say r equals infinity. And one more piece of terminology. The set of all x for which the power series converges this has a name, so this is the interval of convergence. Right? So for any power series, there are these two things. There is the associated radius convergence and the interval convergence. So in that last example I did where I got, -1 to 3, right? That is the interval of convergence, and the radius of convergence in that previous example, r equals 2. So let's try a couple examples now. Okay, so let's find the radius of convergence and interval of convergence for sum n equals 0 to infinity x minus 2 to the n over n plus 1 squared. All right, so the steps will be just as we did before. First, I'm going to apply the ratio test, and then we'll check the endpoints. So first, we do ratio test. Limit as n goes to infinity. I'm going to go straight to flipping and multiplying. So this will be x minus 2 to the n plus 1 divided by n plus 2 squared, times n plus 1 squared over x minus 2 to the n. And so let's see what I can cancel. I can cancel some factors of x minus 2. So this will be the limit as x goes to infinity. Absolute value x minus 2 times n plus 1 over n plus 2 squared. As x goes to infinity, inside these parentheses right here, that's approaching 1. And so what we get is just absolute value of x minus 2. And according to the ratio test, what we need then is for that to be strictly less than 1. And notice, well, I'm about to erase this, so let's just say this series we know converges for all values of x for which absolute value of x minus 2 is less than 1. And I just erased that part right there. We are looking at our radius of convergence right there. Our radius of convergence is 1. So right here, so we can write that down, radius of convergence equals 1. Okay, so now we need to find the interval of convergence. And so let's write this out. X minus 2 has to be between plus and minus 1. That's getting rid of the absolute value part. Add 2 to both sides. And we can see then that as long as x is between 1 and 3, we're guaranteed convergence. Now we need to check the endpoints. When x equals 1, let's see if I take 1 and plug it into here, we get sum n equals 0 to infinity, minus 1 to the n over n plus 1 squared. You can check, this is easy to see, this is an alternating series that converges by alternating series test. On a test or a quiz, you want to actually show the work, but I want to get through this. So converges by alternating series test. When x equals 3, sum n equals 0 to infinity, 1 over n plus 1 squared. Notice this is the same as the sum n equals 1 to infinity of 1 over n squared. This converges right by the p test where p equals 2. So this series converges at both endpoints, which means that our interval of convergence is the closed interval from 1 to 3. So let's try one more example. So sum n equals, this one's kind of a famous example here. Sum n equals 0 to infinity, minus 1 to the n, x to the 2n, divided by 2n factorial. In fact, once we get the result here for the interval and radius of convergence, we'll actually need that a little later on, later in the quarter. All right, so let's do the ratio test. So I'm going to do limit as n goes to infinity, absolute value, x, well, okay, fine, there's a minus 1 to the n plus 1, x to the 2n plus 2 over 2n plus 2 factorial times, so I'm going to flip and multiply, so this will be a 2n factorial over minus 1 to the n, x to the 2n. Now, off to the side, hopefully everyone's had some good practice with canceling factorials. I want to write down the answer right here, so let me just show you how the factorials cancel. 2n factorial means 1 times 2 times 3. Keep going until you eventually get to the number 2n. 2n plus 2 factorial, would look like this. 1 times 2 times 3. Keep going. Eventually we'll get to 2n. The next number is 2n plus 1, and the very last number is 2n plus 2. So when you cancel, you're left with a 2n plus 1 and a 2n plus 2. So here's what we'll get is a limit as n goes to infinity. The minus ones, all that negative stuff is gone because of the absolute value. We're left with an x squared in the numerator and a 2n plus 1 times 2n plus 2 in the denominator. Now, as n goes to infinity, what happens to this fraction? Well, the denominator is getting larger and larger and larger. That limit is equal to 0, which we know is always equal to, or always less than 1. So what we get, the radius of convergence is equal to infinity, and the interval of convergence is all real numbers, so minus infinity to infinity.